Hello friends, welcome back. In this session, we discuss the way of approximating complicated functions with simpler ones that give the accuracy we want for specific applications and are easier to work with. For this purpose, we fix a point on the graph of the function and approximate the graph of the given function by tangent line to the curve at that point. The equation corresponding to the tangent line will be the approximate function to the given function at the fixed point. As the equation of tangent line is linear, this approximation is called linearization. Let us begin with noting that the function f of x is equal to x square, whose graph is a parabola, is differentiable everywhere with its derivative given by f prime x is equal to 2x. In particular, it is differentiable when x is equal to x naught is equal to 1. Then the tangent to the parabola at the point ordered where x naught f of x naught, which is equal to ordered where 1 1, is obtained by the formula y minus f of x naught is equal to f prime x naught times x minus x naught. Since f prime x naught is equal to 2 x naught is equal to 2 times 1, which is equal to 2, the above equation of the tangent line gives y minus 1 is equal to 2 times x minus 1, that is y is equal to 2x minus 1. We draw the parabola y is equal to x square and the tangent y is equal to 2x minus 1 to the parabola at the point ordered where 1 1. If we sufficiently magnify the portion of the parabola and the tangent line near the point ordered where 1 1, it can be seen that the portion of the graph of the parabola near ordered where 1 1 takes on the appearance of the segment of the tangent line y is equal to 2x minus 1. As the portion of the parabola near ordered where 1 1 is very close to the line, we say that the parabola is locally linear at x naught is equal to 1. In other words, the line y is equal to 2x minus 1 locally approximates the parabola y is equal to x square near the point ordered where 1 1. This approximation is called the local linearization. In this case, if we take a point A very near to x is equal to 1, its function value f of a is equal to a square will be very near to the value of 2a minus 1. This is illustrated in the figure. From the figure, it can also be seen that if a point B is far away from x is equal to 1, the values of b square and 2b minus 1 may not be close to each other. This shows that the tangent line only approximate function values very near to x is equal to 1. This justifies why we call this approximation local. As observed in the case of the parabola above, the line that best approximates the graph of f in the vicinity of the point P with coordinates ordered where x naught f of x naught is the tangent line to the graph of f at x naught given by the equation y is equal to f of x naught plus f prime x naught times x minus x naught, provided f prime of x naught exists. If f is differentiable at x is equal to x naught, then the approximate function L of x is equal to f of x naught plus f prime of x naught times x minus x naught, we call it equation number 1, is the linearization or local linearization of f at x naught. The approximation f of x approximately equal to L of x equal to f of x naught plus f prime of x naught times x minus x naught, we call it equation number 2, of f by L is the local linear approximation of f at x naught. The point x is equal to x naught is the center of the approximation. The absolute value of the error at a point x is given by E of x is equal to absolute value of f of x minus L of x. Letting delta x is equal to x minus x naught, we have x is equal to x naught plus delta x, and equation 2 gives f of x naught plus delta x approximately equal to f of x naught plus f prime of x naught times delta x. We call it equation number 3. As an example, we find the local linear approximation of f of x is equal to square root of x at x is equal to x naught is equal to 9, and use it to approximate square root of 9.02, square root of 8.82 and square root of 10. We evaluate the equation L of x is equal to f of x naught plus f prime of x naught times x minus x naught for f of x is equal to square root of x, which is equal to x raised to half at x naught is equal to 9. We have f of 9 is equal to square root of 9, which is equal to 3, and also with f prime of x is equal to 1 by 2 times x to the power minus half, which is equal to 1 by 2 root x. We have f prime of 9 is equal to 1 by 2 root 9, which is equal to 1 by 2 times 3, which is equal to 1 by 6, and the linearization is L of x, which is equal to f of x naught plus f prime of x naught times x minus x naught, which is equal to 3 plus 1 by 6 times x minus 9. That is, the local linear approximation of f of x is equal to square root of x at x naught is equal to 9 is L of x is equal to 3 plus 1 by 6 times x minus 9. Hence, when x is very near to x naught is equal to 9, then f of x approximately equal to 3 plus 1 by 6 times x minus 9. That is, square root of x is approximately equal to 3 plus 1 by 6 times x minus 9. Now, to find approximate value of square root of 9.02, we put x is equal to 9.02 in the above expression and get square root of 9.02 is approximately equal to 3 plus 1 by 6 times 9.02 minus 9. That is, square root of 9.02 is approximately equal to 3 plus 0.02 by 6, which is equal to 3.003333, etc. If we calculate square root of 9.02 directly using a calculator, we obtain square root of 9.02 is equal to 3.00333315 and so on. We see that up to 5 decimal places the values are the same. Absolute value of the error at x is equal to 9.02 is E of 9.02 is equal to absolute value of f of 9.02 minus L of 9.02, which is equal to 0.000015 and so on. Similarly, putting x is equal to 8.82 and x is equal to 10 in the expression square root of x approximately equal to 3 plus 1 by 6 times x minus 9, we find that square root of 8.82 is approximately equal to 3 plus 1 by 6 times 0.18, which is equal to 2.97, and square root of 10 is approximately equal to 3 plus 1 by 6 times 1, which is equal to 3.16666 and so on. Using a calculator, the values can be found to be square root of 8.82 is equal to 2.9698485 and square root of 10 is equal to 3.1622777. Finding absolute value of the errors are left as an exercise. We show that if x is close to 0, then sin x is approximately equal to x and then approximate sin 2 degree. Since we are interested in approximating sin x for values of x very close to 0, we compute the local linear approximation of f of x is equal to sin x at x naught is equal to 0. With f of x is equal to sin x, f prime x is equal to cos x and x naught is equal to 0, the linear approximation is sin x is approximately equal to sin 0 plus cos 0 times x minus 0, which is equal to 0 plus 1 times x. which is equal to x. We bring the attention of the learner that in the approximation sin x is approximately equal to x, the variable x is in radian measure. So, we must first convert 2 degree to radians before we apply this approximation. Since 1 degree is equal to pi by 180 radians, we have that 2 degree is equal to 2 times pi by 180, which is equal to pi by 90, which is approximately equal to 0.0349066. Since sin x is approximately equal to x, it follows from the above that sin 2 degree is equal to sin of 0.0349066, which is approximately equal to 0.0349066. The approximation obtained using a calculator is sin 2 degree is approximately equal to 0.0348995. We now show that when x is very near to 0 and k is any real number, then 1 plus x to the power k is approximately equal to 1 plus kx. This is a useful and important linear approximation for roots and powers, provided x is very near to 0. With f of x is equal to 1 plus x to the power k, f prime of x is equal to k times 1 plus x to the power k minus 1 and x naught is equal to 0. We have f of 0 is equal to 1 plus 0 to the power k, which is equal to 1. F prime of 0 is equal to k times 1 plus 0 to the power k minus 1, which is equal to k, and the linear approximation is 1 plus x to the power k is approximately equal to 1 plus k times x minus 0, which is equal to 1 plus kx as desired. In this session, we discussed linearization, the method of approximating functions locally by linear functions whose graph is the tangent line to the graph of the function at a given point. In this session, we describe differential of a function, formulas for differentials, geometrical interpretation of the differential and estimation of change with the differentials are discussed in this session. The concepts of absolute change, relative change and percentage change in f as we move from a point x naught to a nearby point x naught plus dx are also illustrated through examples. Differentials. The German mathematician Gottfried Wilhelm Leibniz used the notation dy by dx to denote the derivative of y with respect to x. Now, our goal is to define the symbols dy and dx called differentials of x and y respectively in such a way that dy by dx can be treated as an actual ratio. To this, assume that f is differentiable at a point x, define dx to be an independent variable that can have any real value and define dy by the formula dy is equal to f prime x times dx. If dx is different from 0, then we can divide both sides of the above equation by dx to get dy by dx is equal to f prime x. The above expresses f prime of x as the ratio of dy and dx. Formula dy by dx is equal to f prime x is said to express dy is equal to f prime x times dx in differential form. We sometimes write df is equal to f prime x dx in place of dy is equal to f prime x dx and call df the differential of f. For instance, if f of x is equal to 7x square minus 5, since f prime x is equal to 14x, it follows that df is equal to 14x dx. We now discuss some formulas for differentials. If we take f of x is equal to c, a constant function, then f prime x is equal to 0, so that df is equal to f prime x dx gives df is equal to 0 times dx, that is dc is equal to 0. Similarly, it can be shown that d of Cu is equal to C times du. This is the constant multiple rule for differentials. Now, taking f of x is equal to u of x plus v of x, where u of x and v of x are two functions of x, we have by the sum rule of differentiation f prime x is equal to u prime x plus v prime x, and hence df is equal to f prime x dx becomes df is equal to u prime x plus v prime x times dx. Since u prime x is equal to du by dx and v prime x is equal to dv by dx, we have u prime x dx is equal to du and v prime x dx is equal to dv, and hence the above gives df is equal to du plus dv, that is du of u plus v is equal to du plus dv. This is the sum rule for differentials. Similarly, the following formulas for differentials can be derived. Product rule: d of uv is equal to u dv plus v du. Quotient rule: d of u by v is equal to v du minus u dv by v square, provided v of x is different from 0. Power rule: d of u raised to n is equal to n times u to the power n minus 1 du. As an application of quotient rule, with u is equal to x and v is equal to x plus 1, we find that d of x by x plus 1 is equal to x plus 1 dx minus x times d of x plus 1 all divided by x plus 1 all square, which is equal to x dx plus dx minus x dx all divided by x plus 1 all square, which is equal to dx by x plus 1 all square. The following are the trigonometric identities for differentials. d of sin u is equal to cos u du, d of cos u is equal to negative sin u du, d of tan u is equal to sec square u du, d of cot u is equal to negative cosec square u du, d of sec u is equal to sec u tan u du, d of cosec u is equal to negative cosec u cot u du. As an example, with u is equal to 2x, the above gives d of tan 2x is equal to sec square 2x d of 2x, which is equal to 2 times sec square 2x dx. We now discuss the geometrical interpretation of the differential. Let f of x be differentiable at x is equal to x naught. We are going to see the method to predict how much the value of f of x naught will change if we move to a nearby point x naught plus dx. If dx is small f and its linearization given by the equation of the tangent L of x is equal to f of x naught plus f prime of x naught times x minus x naught will change by nearly the same amount. Since the values of L of x are simple to calculate, calculating the change in L offers a practical way to estimate the change in f. The change in f is delta f is equal to f of x naught plus dx minus f of x naught. The corresponding change in L is delta L is equal to L of x naught plus dx minus L of x naught, which is equal to f of x naught plus f prime of x naught times x naught plus dx minus x naught, we call it L of x naught plus dx minus f of x naught plus f prime x naught times x naught minus x naught, we call it L of x naught, which is equal to f of x naught plus f prime of x naught times dx minus f of x naught, which is equal to f prime of x naught dx. Thus, the differential df is equal to f prime of x naught dx can be geometrically interpreted as follows. When df is evaluated at x is equal to x naught, then df is equal to delta L, which is the change in the linearization of f corresponding to the change dx. Estimation of change with differentials. Let f of x be differentiable at x is equal to x naught. The approximate change in the value of f when x changes from x naught to x naught plus dx is df is equal to f prime of x naught dx. As an example, we consider a circle of radius r. If radius r increases from r naught is equal to 5 meter to r naught plus dr is equal to 5.2 meter, then estimate the increase in the circle's area A by calculating dA. We also compare this value with the true change delta A. Here the function is A of r is equal to pi r square, which is the area of a circle of radius r. The approximate change in the value of A of r when r changes from r naught to r naught plus dr is dA equal to A prime r naught times dr. Here A of r is equal to pi r square and r naught is equal to 5 gives A prime r is equal to 2 pi r and A prime r naught is equal to 2 pi r naught, which is equal to 2 pi times 5, which is equal to 10 pi. Also dr is equal to 5.2 minus 5, which is equal to 0.2. Thus, the estimated increase in area is dA is equal to 10 pi times 0.2, which is equal to 2 pi meters square. The true change in area is delta A is equal to pi times 5.2 square minus pi times 5 square, which is equal to 27.04 minus 25 times pi, which is equal to 2.04 times pi, which is equal to 2 pi, which is dA, plus 0.04 pi, which is the error. Hence, the absolute error is 0.04 pi. Now, for the function y is equal to x square, we give the geometrical interpretation of the relationship between the differentials dx and dy when x is equal to 3. Since dy by dx is equal to 2x, we have dy is equal to 2x dx, which is equal to 6 dx when x is equal to 3. This tells us that if we travel along the tangent line to the curve y is equal to x square at the point ordered by 3, 9, then any change of dx units in the horizontal direction produces a change of dy is equal to 2 times 3 times dx, which is equal to 6 dx units in the vertical direction. For instance, a change of dx is equal to 2 units along the x axis, that is x changes from 3 to 3 plus dx, which is equal to 3 plus 2, which is equal to 5, then there will be a rise of dy is equal to 6 dx, which is equal to 6 times 2, which is equal to 12 units along the tangent. That is, y changes from 9 to 9 plus dy, which is equal to 9 plus 12, which is equal to 21. That is, along the tangent from the point ordered by 3, 9, we reach the point ordered by 5, 21. At the same time, a change in 2 units along the x axis changes the point ordered by 3, 9 to the point ordered by 5 square, which is equal to ordered by 5, 25 along the parabola. For a given function y is equal to f of x, we define delta y is equal to f of x plus delta x minus f of x to denote the signed change in y from its value at some initial number x to its value at a new number x plus delta x. It is important to understand the distinction between the increment delta y and the differential dy. To see the difference, let us assign the independent variables dx and delta x the same value, so that dx is equal to delta x. Then delta y represents the change in y that occurs when we start at x and travel along the curve y is equal to f of x until we have moved delta x is equal to dx units in the x direction, and dy represents the change in y that occurs if we start at x and travel along the tangent line until we have moved dx is equal to delta x units in the x direction. From the figure, it can be seen that the values delta y and dy may be different in general. As an example, we find dy and delta y at x is equal to 3 with dx is equal to delta x is equal to 2, where y is equal to square root of x. With f of x is equal to square root of x, we obtain delta y is equal to f of x plus delta x minus f of x, which is equal to square root of x plus delta x minus square root of x, which is equal to square root of 5 minus square root of 3, which is approximately equal to 0.504. If y is equal to square root of x, then dy by dx is equal to 1 upon 2 square root of x, so that at x is equal to 3, dy is equal to 1 upon 2 square root of x dx, which is equal to 1 upon 2 square root of 3 times 2, which is equal to 1 upon square root of 3, which is equal to 0.577. Absolute, relative and percentage change. We now discuss absolute change, relative change and percentage change in f as we move from x naught to a nearby point x naught plus dx. True value of absolute change in f is delta f is equal to f of x naught plus dx minus f of x naught, and estimated value of absolute change in f is df is equal to f prime of x naught times dx. True value of relative change in f is delta f by f of x naught, and estimated value of relative change in f is df by f of x naught. True value of percentage change in f is delta f by f of x naught times 100, and estimated value of percentage change in f is df by f of x naught times 100. As an example, we now show that the relative error in computing the volume of a sphere due to an error in measuring the radius is approximately equal to the 3 times the relative error in the radius. Let V be the volume and R be the radius of the sphere. Then they are related by the equation V is equal to 4 by 3 times pi r cube. Taking logarithms on both sides, we obtain log V is equal to log of 4 by 3 pi plus 3 log r. The differential of a constant is 0. Hence, the differential of log of 4 by 3 pi is 0. Thus, taking differentials, the above equation yields 1 by V times dV is equal to 3 times 1 by r dr, which is dV by V is equal to 3 times dr by r. Hence, the error relation is delta V by V is equal to 3 times delta r by r, where delta V by V is the relative error in computing the volume and delta r by r is the relative error in computing the radius. The error relation delta V by V is equal to 3 times delta r by r simply says that the relative error in computing the volume of a sphere due to an error in measuring the radius is approximately equal to 3 times the relative error in the radius. As another example, suppose the radius r of a circle increases from r naught is equal to 10 meters to 10.1 meters. We estimate the percentage change in the area. Here, A of r naught is equal to pi r naught square, which is equal to pi times 10 square, which is equal to 100 pi, and dr is equal to 0.1. So, dA is equal to A prime r naught times dr, which is equal to 2 pi r naught times dr, which is equal to 2 pi times 10 times 0.1, which is equal to 2 pi meter square. Hence, dA by A of r naught times 100 is equal to 2 pi by 100 pi times 100, which is equal to 2%. As another example, the radius of a sphere is measured with a percentage error within plus or minus 0.04 percentage. Estimate the percentage error in the calculated volume of the sphere. The volume of a sphere having radius r is V is equal to 4 by 3 pi r cube. So, taking differentials, we obtain dV is equal to 4 pi r square dr. It then follows from the formulas for V and dV that dV by V is equal to 4 pi r square dr all divided by 4 by 3 pi r cube, which is equal to 3 times dr by r. If dr denotes the error in measurement of the radius of the sphere, then the relative error in this measurement is estimated by the ratio dr by r, where r is the measured value of the radius. Our assumption is that the percentage error in this measurement is within plus or minus 0.04 percentage, then becomes minus 0.0004, which is less than or equal to dr by r, which is less than or equal to 0.0004. Multiplying each term by 3 gives the equivalent inequalities negative 0.0012, which is equal to 3 times negative 0.0004, which is less than or equal to dV by V, which is less than or equal to 3 times 0.0004, which is equal to 0.0012. Since we are using dV by V to approximate the relative error in the calculated volume of the sphere, we estimate this percentage error to be within plus or minus 0.12 percentage. As another example, let the volume V of fluid flowing through a small pipe or tube in a unit of time at a fixed pressure is a constant time the third power of the tube's radius r. We are going to show that how much the value of V will be affected by a 10% increase in r. Here we take V is equal to k r cube, where k is a constant. Taking differentials on both sides, we get dV is equal to 3 k r square dr. Hence, dV by V is equal to 3 k r square dr all divided by k r cube, which is equal to 3 times dr by r. So, the relative change in V is 3 times the relative change in r. So, a 10% increase in r, that is dr by r times 100, which is equal to 10%, implies dV by V times 100 is equal to 3 times dr by r times 100, which is equal to 3 times 10%, which is equal to 30%. Hence, a 10% increase in the radius of the pipe will produce a 30% increase in the flow of fluid through the pipe. In this session, we described differential of a function. Through a number of examples, the concepts of absolute change, relative change and percentage change in f as we move from a point to a nearby point have been illustrated. Hope this session is beneficial to you. See you next time. Have a great day.